Hello everyone, myself Bhuvnesh Kumawar, and we are continuing our modern algebra lecture series. In previous two lectures, we have covered quasi-group, semi-group, monoid group, abelian group, order of element, order of a group. These topics we have already covered. You can check in playlist. Now today we are going to cover subgroup and few theorems of subgroup. So what is subgroup? Subgroup is a non-empty subset of a group G, that is H, with same binary operation. If this subset is satisfied all basic property of the group, then we will call it subgroup. So if we take H is a subset of G, then if G dot is a group and H dot is also a group, then we will call H is a subgroup of G. Okay, that, that is a basic definition of subgroup. So, for example, if you take a group or a set Q is equal to P by Q, such that P and Q belongs to integer, then this Z is a set of integer is subset of this Q with this binary operation multiplication. This is subgroup of G. Okay. So, for example, if you take a group G is equal to 1 minus 1, 1 minus iota. If we take this group and H is equal to 1 and minus. If we take this is subset, H is a subset of G. Now we will check four basic properties. First is closure property. If we take 1 dot minus 1, that is equal to minus 1, that belongs to H. So closure property is satisfied. Second is associativity. If we take 1 dot minus 1 dot 1 is equal to 1 dot minus 1 dot 1. So associativity is also satisfied. Third property is identity element. If we take minus 1 dot E is equal to minus 1, that means E is equal to 1. So 1 belongs to H. So identity element is also in same set H. What is inverse? For inverse, if we check minus 1 dot minus 1, that is equal to 1. Okay, that is equal to identity element. So here minus 1 is the inverse of minus 1. Okay, similarly, 1 is inverse of 1. So all four basic property of a group is satisfied in this set H. Then we will call it subgroup of this group G. Now we will take few theorems of subgroup. These are basic fundamental theorem of subgroup. The first is if H is a subgroup of a group G, then H inverse is equal to H. That we have to prove. So here we have to prove that given that H is a subgroup of G. Now we have to prove that H inverse is equal to H. So from this, first we will define H inverse. H inverse is equal to small h inverse such that H belongs to H. Okay. So now we have to prove that H inverse is equal to H. That we have to prove. So given that H is a subgroup of G, so this H will satisfy all four basic property of a group. So if H belongs to H, that implies H inverse should also belongs to H by by inverse property. Okay. So from this we can write From this we can say if we take H inverse belongs to capital H inverse. Okay. Now if we take this H inverse, okay, तो यहाँ पे क्या अप्रोच क्या रहेगी हमारी, इस जब भी हमें दो सेट को इक्वल प्रूव करना है तो आवर अप्रोच विल बी H inverse is subset of H. If H is a subset of H inverse. From these two we can write H1 is equal to H. We can write. Okay. So first we will take H inverse belongs to H. Okay. Now we know that this H inverse also belongs to, and we know that H inverse belongs to H also. That implies H inverse is subset of H. Okay. Now we will take H belongs to capital H. Okay. If you take H belongs to capital H, then H inverse also belongs to H. Okay, by inverse property. From this, we can write H inverse belongs to H inverse also. By definition of this H inverse. From this, we can write H is a subset of H inverse. So from this 1 and 2, from 1 and 2, we can say H1 is equal to H. ओके, तो ये सिंपल है। और यहाँ पे हम इससे भी ले सकते थे कि गिवन दैट दिस इज गिवन, सो इसका इन्वर्स लीजिए। सो इफ यू टेक H inverse belongs to H, so then by definition of capital H inverse, we can say H inverse whole inverse should belongs to H inverse. That implies H belongs to H inverse. So from this from this we from this we initially we take H belongs to capital H. That means H inverse belongs to H. From this we got H belongs to capital H inverse. So from this we can say H is a subset of H inverse. ठीक है, ये यहाँ से भी कर सकते हैं। तो इन दो से हम ये ले सकते हैं कि H inverse is equal to capital H. Now next theorem. If H is any subgroup of G, then HH is equal to H. That is second theorem. So here we have to prove that given that H is a subgroup of G, and we have to prove that HH is equal to H. First we will define what is HH. HH is small h1, small h2, such that h1 and h2 belongs to capital H. Okay, and given that H is a subgroup of G, that is given. So if H is a subgroup of G, then this H will satisfy all these four basic property of the group. Now, if we take here, our approach will be same. First we will prove HH is subset of H, then H is a subset of HH. From these two, we can say HH is equal to H. So, by definition of HH, if we take A and B belongs to H, then by definition of HH, AB belongs to HH. Okay. But given that H is a subgroup of G, so by closure property we can say AB belongs to H. So from these two, initially we took that AB belongs to HH, and we ended with AB belongs to H. That means HH is subset of H. Okay, call it equation 1. Now, second part, this is first part. The second part, if we take A and B belongs to H, then by closure property we can say A, B belongs to H. Okay, but these are multiplication to element of H, so that that will also belongs to that AB also belongs to HS. So from this we can say H is subset of HH. Okay, because we started from this and ended with this, so that means H is a subset of capital H. So call it equation 2. Now from equation 1 and 2 we can write HH is equal to H. Else 2. Now next year. Next year is the test. First is two-step test, then second is one step. In this test, if subset is given, if we have a group G and there is a subset of group G, then we have to check that this subset is a subgroup or not. Then we will check these two properties, that is closure property and inverse property. If A belongs to H and B belongs to H, that means AB belongs to H, and A belongs to H, that means A inverse belongs to H. These two properties we will check. If these two properties is satisfied, that means that given H is subgroup of H. So here we have to prove that H is a subgroup of G. If and only if AB belongs to H and A inverse belongs to H, when AB belongs to H. So first we will take these two conditions. We will prove that H is a subgroup of H. Then we will take H is a subgroup of G. Then we will prove these two conditions. So first we will take necessary condition. Necessary condition, given that A B belongs to H, that implies A B belongs to H and A inverse belongs to H. That is given. Now we will check four properties of group. First is closure property. So that is given. That is given in condition. If A and B belongs to H, it implies AB belongs to H. So closure property is satisfied here. Now second is inverse. So if A belongs to H, that implies A inverse belongs to H. That is also given. These two are given. So inverse and closure properties are satisfied. Now we will check identity element. Third is identity element. For that, if we take A belongs to H and A inverse belongs to H. Okay. So by second property, we can write if A belongs to H, A inverse also belongs to H. Now by closure property, we can write A dot A inverse should belong to H. That means identity element belongs to H. So identity element is also in same set H. So now fourth is associativity. So for associativity, if we take A B dot C is equal to A dot C A dot B dot C, that will also satisfy. So all base four basic property of group is satisfied in this given subset H, then we will call it subgroup of G. So that means from these four property we can say H is a subgroup of G. The first part is true. Now we will go for sufficient condition. Sufficient condition. That means given that H is a subgroup of G. That is given. From this we can say that H will satisfy all four basic property of the group. That means by closure property we can write by closure we can write A B belongs to H. That means A dot B belongs to H. That is first. And by second inverse axiom, we can say if A belongs to H, that means A inverse belongs to H by inverse axiom. So these two also satisfy. So we have proved necessary condition and we have also proved sufficient condition. So this is two-step test. Now next is the one-step test. In this, we have to prove that H is a subgroup of G if and only if AB belongs to H. Means if we assume that AB belongs to H, that means H is a subgroup of G. And second, if H is a subgroup of G, then we will prove that AB inverse belongs to H. Okay? So first we will take necessary condition. For that, given that AB inverse belongs to H, where A and B belongs to H. Okay? That is given, right? From this, we will check for properties of group. Okay, given that AB inverse belongs to H, that is given. So from this, if we take A and A belongs to H, then by this given condition, we can write A inverse should also belong to H. That means identity element E belong to H. So first is identity element. Now second is inverse. Now we'll check inverse. For that, if we take two elements, A and A, B, and C, these three elements belong to H. Given that AB belongs to H, that implies AB belongs to AB inverse belongs to H, and identity element भी सी H element H सेट के अंदर होगा. So from this if we take E dot B inverse belongs to H from this property, from this given condition. If we take A is equal to E, then we can write E B inverse belongs to H. From this we can write B inverse belongs to H. Okay, so inverse property also satisfied here. Now next is third is closure. Closure. If we take A and B belongs to H, that implies A inverse and B inverse should also belong to H. Okay, by this second property that we have already proved. From this, if we take two elements B in A and B inverse, okay, belongs to H, then we can write A dot B inverse whole inverse should belong to H from this given condition. Okay, here we are taking first element A, second element is B inverse, then we can write A, B inverse, whole inverse belong to H. From this we can write AB belongs to H. Okay, so closure property is also satisfied here. तीन property satisfy हो गई. Now fourth is associativity. If it obviously satisfy here. So associativity, if we take A dot B dot C, that will be equal to A dot B dot C. So all four basic properties satisfy. If given that AB inverse belongs to H, then we can say this given subset H is subgroup of G. Okay, first part is true. Now we will go for second. That is sufficient condition. So sufficient condition के क्या है? Given that H is a subgroup of G, that is given. So now we have to prove that AB inverse belongs to H. अगर देखो H is a subgroup of G, that is given. अगर ये दिया हुआ है, so if we take A and B belongs to H, then we can say A inverse and B inverse should also belong to same set H by inverse axiom. Now, if we take two elements A and B inverse belongs to H, then by closure property we can say A dot B inverse belongs to H. ठीक है, by closure property. ठीक है, सेकेंड पावर भी प्रूव हो गया. सो ये वन स्टेप is very useful for proving that a given subset is a subgroup or not. Now, next theorem is a necessary and sufficient condition for a non-empty subset H of a group G to be subgroup of G is that H inverse is a subset of H. So here, given that if we have to prove that H is a subgroup of G, if and only if H is a subset of H. We will assume that this is true, then we will prove that H is a subgroup of G, then we will take H is a subgroup of G, then we will prove that this condition is true. So first we will take necessary condition. Okay. So necessary condition that given that H inverse is subset of H. Okay. Where H is inverse is defined as H1 H2 inverse such that H1 H2 belongs to capital H. That is given. That is definition of H inverse. Now, if you take A and B belongs to set H, then a definition of capital H inverse, we can say A B inverse belongs to H. ओके, मतलब यहाँ पे H को H में से एक एलिमेंट A ले लीजिए, H इनवर्स में से एक एलिमेंट B ले लीजिए. तब यहाँ पे जो H है, H कोई सेट है एंड जो H इनवर्स है वो है यहाँ पे H इनवर्स सच दैट H बिलोंग्स टू कैपिटल H. सो हमने जो H है H में से कोई एलिमेंट ले लिया A, तो इसका इनवर्स होगा वो H इनवर्स में भी होगा, H इनवर्स में होगा A इनवर्स, और H में अगर हम B ले लेते हैं तो उसमें B इनवर्स होगा. ठीक है, तो ऐसे ही हमने यहाँ पे ले लिया कि H में से हमने A लिया और H इनवर्स में से हमने B, H में से हमने दो ले लिया, B लिया, ये जो H सेट है उसमें से हमने A एंड B ले लिया. सो फ्रॉम दिस डेफिनेशन वी कैन से A B इनवर्स बिलोंग्स टू H H. ठीक है, क्योंकि A और B एलिमेंट है H के, तो H इनवर्स में B इनवर्स जाएगा. तो फ्रॉम दिस वी कैन से A B इनवर्स बिलोंग्स टू H H. ठीक है, बट गिवन दैट H H इज a subset of H and this is subset of H, that implies A B belongs to H, and by one step test we can say H is a subgroup of H. ठीक है, so that is necessary condition. Now we will take sufficient condition. Now sufficient condition. So sufficient condition, given that H is a subgroup of G. If H is a subgroup of G, then if A and B belongs to H, then we can, if we take A B inverse belongs to H inverse. Okay, but by the subgroup property, by subgroup property, we can say AB1 belongs to H. Okay, by one step test. So from this we can say H inverse is subset of H, hence proof. ठीक है, दोनों कंडीशन हमने यहाँ पे चेक कर ली है कि H is a H1 is a subset of capital H. Now next theorem we will take. Earlier we proved that H inverse is subset of H that we have proved. Now we will prove that H inverse is equal to H. तो इसी को आगे हम परस्यू करेंगे. फर्स्ट पार्ट तो सेम ही हो जाएगा, सेम एज दिस वन. नाउ we have proved that H inverse is a subset of H. Now by theorem 40, we have proved that necessary condition. We have already proved that H, if H inverse is equal to H. Okay, that implies if we take a element, if we take A, B inverse belongs to H, by definition of H inverse from this, that is equal to H. For necessary condition given that H inverse is equal to H, that is given for necessary condition, that is given. So we have to prove that H is a subgroup of G. So from this, by definition of capital H inverse, we can say AB inverse belongs to capital H inverse, that is equal to H. That means AB inverse belongs to H. So by one step test, we can say H is a subgroup of G. Now sufficient condition. Again, here we have to prove that H inverse is equal to H. That means we have to prove that H inverse is subset of H. Then H is a subset of H inverse. By these two, we can write H inverse is equal to H. Okay. So here, given that H is a subgroup of G for sufficient condition. Now, by closure property, by one step test, by fourth theorem, this by this using this theorem, we can write if H is a subgroup of G, then we can write A B inverse belongs to H. But by definition of H inverse, A B inverse belongs to H inverse also. ठीक है? From this we can say, we assume that by definition AB inverse is belongs to H inverse, and by one step test AB inverse belongs to H. That means this H inverse is subset of H. ठीक है? Earlier, first we have taken this element AB inverse that belongs to H inverse by definition of H inverse. But given that H is a subset of G, that means this condition will be satisfied. That means H inverse is a subset of H. Now, secondly, if we take two elements, A and B belongs to H, okay, that implies A inverse and B inverse would also belongs to H because H is a subgroup. That means if we take two elements A and B inverse belongs to H, okay, then by closure property, A B inverse belongs to H. There is a comma. Okay. By closure property, we can say this, but by the definition of H inverse, this by definition of H inverse, is A B belongs to H inverse. Okay. So we started from this, we ended here, then we can say this H is a subset of H inverse. So call it this equation 1 and this equation 2. From 1 and 2, we can write H is equal to H inverse. Hence 2. Now, next theorem is a necessary substitute condition for a finite complex edge or subset edge of a group G to the subgroup of G if AB belongs to H, that implies AB belongs to H. That is closure property. So there is a given that this is necessary and sufficient condition, means if and only if condition. So H is a subgroup of G if and only if AB belongs to H, that implies AB belongs to H. So first we assume that this is true, then we will prove H is a subgroup of G, then we will take H is subgroup of G, then we will prove this. So first is necessary condition. So necessary condition, given that A and B belongs to H, that implies AB belongs to H. So first we will check closure. So closure is already given. पहले से ये हुआ है. If A and B belongs to H, that implies AB belongs to H. Okay, that is given. Now second, that is closure. Now here is a given that this is subset. This subset is a finite. That is very important. This is important. So if we take A belongs to H, that means if we operate A dot A should also belong to H by closure property. That implies A square belongs to H. Similarly, we can say A, A square, A cube, so on belong to H. ठीक है, by closure property. Now, given that this is finite group, for finite मतलब ये फाइनाइट तभी हो सकता है कि एक सर्टेन इंटरवल के बाद में ये टर्म्स रिपीट होना स्टार्ट कर देंगे, नहीं तो ये इनफाइनाइट हो जाएगा. तो इसकी लिमिटेशन कुछ नहीं है कि ए रेस्ट पावर वन हुआ, टू हुआ, थ्री हुआ, फोर हुआ, इनफाइनाइट हो जाएगा. तो इनफाइनाइट नंबर हो जाएंगे. बट हेयर गिवन दैट दिस सबसेट is a finite subset. So for finite subset, we can take two elements a raised to power r and a raised to power s is equal. Here these two elements are equal. From this we can write a raised to power r minus s is equal to a raised to power 0, that is equal to identity element. Or we can take r minus s is equal to n, where n is least positive integer. So if n is least positive integer, then a raised to power n is e, then this n is the order of that element a. Okay, that is the definition of order of element. So ये आइडेंटिटी एलिमेंट भी इस सेट में लाई कर रहा है. तो सेकंड इज आइडेंटिटी एलिमेंट इज आल्सो सेटिस्फाइड. नाउ थर्ड इज इनवर्स. For inverse, if we take a raised to power p element of this set H, now we operate a raised to power q, that is equal to identity element, that is a raised to power n. From this we can write a raised to power q is equal to a raised to power n minus p. So this a raised to power q is the inverse element of a raised to power p. So here n minus p is less than equal to, it will be between 0 and n. So inverse element is also exist. Now fourth property is associativity. वो तो satisfy होगी होगी. Means if we take three elements x, x dot y dot z is equal to x dot y dot z, that is equal to, suppose a raised to power p plus q plus r. So x is equal to a raised to power p, y is equal to a raised to power q, z is equal to a raised to power r. That will also satisfy. So all four basic property of a group is satisfied in this given subset H, then we will call it subgroup. So from this, we can say H is a subgroup of G. That is necessary condition. Now we will go for sufficient condition. Sufficient condition. So sufficient condition given that H is a subgroup of G. That is given. Now by closure property, we can say if A and B belongs to H, then AB belongs to H by closure property. Okay. So sufficient condition is also satisfied here. So from these two, we can say that H is a subgroup of G if AB belongs to H. That is important. We will use this property in our subsequent theorem and example. Next is this is very good example. This is important and good. So here H and K are two subgroup of a group G. मतलब H और K किसी group G के subgroup है. Now HK is a subgroup of G if and only if HK is equal to KH. So here we have to prove that HK is a subgroup of G if and only if HK is equal to KH. That we have to prove. So given that H is a subgroup of G and K is a subgroup of G, that is given. Quality equation 1. Now first we take necessary condition. So necessary condition that given that HK is equal to KH, that is given. ओके. अच्छा, पहले हम डिफाइन कर लेते हैं के एच के है क्या. एच के इज इक्वल टू स्मॉल एच स्मॉल के सच दैट H1 बिलोंग्स टू H, K1 बिलोंग्स टू K. ठीक है. और यहाँ पे जो एच के है, एच के कैपिटल एच के है यहाँ पे, दैट इज इक्वल टू स्मॉल एच स्मॉल के, स्मॉल H1 स्मॉल K1. और जो कैपिटल के एच है दैट इज इक्वल टू K2 H2 और मन H3. जरूरी नहीं है दोनों सेम ही हो, H3 कुछ भी हो सकता है. लेकिन जो एच जो स्मॉल एच है वो कैपिटल एच से आएगा, जो स्मॉल के है वो कैपिटल के से ही आएगा. तो वेयर स्मॉल के बिलोंग्स टू कैपिटल के एंड स्मॉल एच बिलोंग्स टू कैपिटल एच. ठीक है. सो वी विल यूज वन स्टेप टेस्ट here. If we take HK and HK inverse, okay, these two are two different. मतलब लाइक जैसे हम लेते थे कि दो एलिमेंट लेते थे, कि सपोज अगर हम लेते थे A and B belongs to H, then if AB inverse belongs to H, then we will call H as a subgroup of G. ये करते थे अगर H के दो एलिमेंट लेते थे A और B, फिर चेक करते थे ए बी इनवर्स अगर H में ही आता है तो जो H है वो G का सब ग्रुप होगा. सो सिमिलरली वी आर टेकिंग A एज ए कैपिटल H के. ठीक है. कैपिटल H के मतलब स्मॉल H1 K1, ये एक एलिमेंट है. सेकेंड इज H के उसका इनवर्स दैट इज H2 K2, इसका इनवर्स ले लीजिए. ठीक है. सो वी विल टेक टू एलिमेंट A as HK and B as another HK. So from this we can write HK, that is K inverse H inverse. तो इनवर्स की प्रॉपर्टी होती है कि अगर A B का इनवर्स ले रहे हैं दैट इज इक्वल टू B inverse A inverse. Similarly we can write HK whole inverse is equal to K inverse H inverse. ठीक है. From this we can write H K K inverse H inverse by associativity we can write. Now from this, अगर हम k के दो एलिमेंट लेते हैं, सपोज k1 and k2 belongs to k, then k1 inverse and k2 inverse should also belongs to k. Okay, should also belongs to k. Then from the closure property, because k is a subgroup, so by closure property we can write k1 k2 inverse should belong to k. तो यही प्रॉपर्टी हम यहाँ पे यूज कर रहे हैं कि k and k inverse is equal to k. Or in our previous theorem we have proved that in this theorem, if H is a subgroup of G, here we have taken that if H is a subgroup of G, that implies H inverse is equal to H. This property we are using in this theorem. Okay, so here K inverse is equal to K, so that is equal to K H inverse. Now, given that HK is equal to KH, that is given. So we will use this second and third. By second and third, we can write HK is equal to KH. KH H inverse from 2 and 3. Okay. Now, by again using that theorem, we can write this H inverse is equal to H. Okay. By using this theorem, we can write from this theorem H inverse is equal to H. So that is equal to KH, or that is equal to HK from 2, equation 2. So we started with this two element and we are operating these two element. We are getting element in this set HK. That means by one step test, we can say HK is subgroup of C. We can say. Okay. That is necessary condition. Now we will prove sufficient condition. Okay. Now sufficient condition. For sufficient condition, given that H is a subgroup of C, that is given. Okay. So if H is subgroup of G, then that implies H inverse is equal to H. Okay. We have already proved this theorem. That is this first theorem. If H is a subgroup of G, that implies H inverse is equal to H. We are using this theorem. By theorem 1, we can write if H is a subgroup of G, then H inverse is also subgroup of H inverse is equal to H. Now again, K is subgroup of G, that implies K inverse is equal to K. Okay. Now, third is given that HK is subgroup of G, that implies HK inverse is equal to HK. Now, from this we can write K inverse H inverse is equal to HK. And from this 1 and 2, we can write K inverse equal to K and H inverse equal to H, that is equal to HK. ठीक है, तो that is sufficient condition. तो हमने necessary condition, sufficient condition दोनों prove कर दिए हैं. Now next is A1 and H1 and H2 are two subgroup of G. Then H1 intersection H2 is a subgroup of G. So here we have to prove that H1 intersection H2 is a subgroup of G. That we have to prove. So here given given that H1 is subgroup of G and H2 is subgroup of C, that is given. ठीक है, और यहाँ पे दो सेट है H1 and H2. These are two subset or subgroup, or that is this is intersection of H1 H2. H1 intersection H2. अगर हम इस H1 intersection H2 में दो एलिमेंट लेते हैं X and Y that belongs to H1 intersection H2. If we take X1, X and Y belongs to H1 intersection H2, that implies XY belongs to H1 and XY belongs to H2. ओके, इंटरसेक्शन का मतलब ये होता है कि दोनों जो सेट है उसमें लाई करेगा ये एलिमेंट. फ्रॉम दिस, given that H1 is a subgroup of G, that means XY inverse belongs to H1, and given that H2 is subgroup of G, that means XY inverse belongs to H2. ठीक है, from these two we can write XY inverse belongs to H1 intersection H2. इंटरसेक्शन होता ही है कि जो दोनों सेट के अंदर बिलोंग कर रहा है वही एलिमेंट इंटरसेक्शन में आ रहा है. सो फ्रॉम दिस वी कैन से बाय वन स्टेप टेस्ट we can say H1 intersection H2 is subgroup of H. Hence proof. Now next theorem, the union of two subgroup of a group is the subgroup if one is contained in another. मतलब कहना क्या चाहते हैं कि दो सबसेट है H1 एंड H2, ठीक है, इन दोनों का यूनियन सबग्रुप तभी होगा जब H1 यूनियन H2 इज इक्वल टू H2 और H1 यूनियन H2 इज इक्वल टू H1. ये दोनों सेटिस्फाई, इन दोनों से कोई कंडीशन सेटिस्फाई होगी तभी वो जो H1 यूनियन H2 है वो सबग्रुप हो सकता है. सो फर्स्ट वी विल टेक necessary condition. Necessary condition means if we take H1 union H2 is equal to H2, means this H2 contains H1 or H1 union H2 is equal to H1. That means that H1 contains H2. ठीक है, that is given. Now, if this condition is satisfied, then we can say H2 is a subgroup of G, that is given if H1 union H2 is equal to H2. That means H1 union H2 is a subgroup of G. Similarly, we can say if H1 is subgroup of G, that means H1 union H2 is a subgroup of G. ठीक है, ये नेसेसरी कंडीशन है. सिमिलरली हम सफिशिएंट कंडीशन भी प्रूव कर सकते हैं. सफिशिएंट कंडीशन प्रूव करने के लिए हमें गिवन दैट H1 union H2 is a subgroup of G, that is given, and we have to prove that either H1 union H2 is equal to H2 or H1 union H2 is equal to H1. That you can do as an exercise, okay, and put it in comment section. Now we will take an example based on this subgroup theory. So H is a finite non-empty, that is a finite, that is important. Okay, non-empty subset of G, then prove that H is a subgroup of G if and only HH HH is a subset of H. So we have to prove that H is a subgroup of G if and only if H is a subset of H. So here we use, given that this is finite non-empty subset. Okay, this is finite, that is given. So first is necessary condition, given that H is subset of H. That means if we take A and B belongs to H, that implies this element A. Okay, this AB belongs to H and this AB belongs to HH also. Okay, that is given. So we have to prove that H is a subgroup. For that, there is a finite non-empty subset. So for finite, we have proved in this theorem, in theorem 7, we have proved that a finite subset is a subgroup if AB belongs to H. Okay, if closure property is satisfied in a subset H, then we will call this subset H as a subgroup of G. So we will use this theorem. So by seventh theorem, so by theorem 7, we can say if uh, given that this is AB belongs to HH, that is subset of H, that implies AB belongs to H. ठीक है, मतलब क्लोजर प्रॉपर्टी सेटिस्फाई होती है यहाँ पे, अगर दिस इज गिवन देन क्लोजर प्रॉपर्टी इज सेटिस्फाइड है. So by seventh theorem, if closure property is satisfied in a given subset H, then we can say that this H is a subgroup of G. Okay, this is necessary part. Now second is sufficient condition that we will prove. So given that H is a subgroup of G, that is given. So we have to prove that H is a subset of H. So from this we can say if we take an element, if A and B belongs to H, then this AB belongs to HH. ठीक है? By definition of HH, we can say that AB belongs to HH. And now this H is a subgroup of G, then this AB belongs to H by closure property. So by these two equations, we can say this HH is a subset of H. Okay. तो हेल्स प्रूफ हमने नेशनल कंडीशन पे प्रूव कर दी, सफिशिएंट कंडीशन पे प्रूव कर दी. सो हमने जो मोस्ट फंडामेंटल थ्योरम है सब ग्रुप की वो सारी कवर कर ली है. इसके बेस कुछ एग्जांपल लिए हैं, आप प्रैक्टिस कर सकते हैं एग्जांपल. ठीक है, सो यही थ्योरम के यूजेस एग्जांपल में लगेंगे जो आपके न्यूमेरिकल प्रॉब्लम सॉल्व करने में हेल्प करेंगे. तो दैट्स इट फॉर दिस लेक्चर. थैंक यू.